In this video, we're going to talk about the square root of a complex number. So first of all, what does it mean to take the square root of a complex number? To answer this question, why don't we think about first what it really means to take the square root of a real number, say the square root of 9. We know that the square root of 9 is 3. But why is it 3? Well, it's 3 because 3 squared is 9. Now, of course, we also have that negative 3 squared is also 9. But the square root fact for that goes as negative root 9 equals negative 3. And we're able to make a distinction because there's an ordering of the real numbers. And the ordering goes negative 3 is less than 3 in this particular case. Okay, so to get a square root fact for a complex number, why don't we stick in a complex number and square that instead of using a real number? So instead of 3 squared equals 9, why don't we go ahead and square a complex number, say a very simple one. How about 1 plus I? So 1 plus I squared, that's just equal to, first of all, we've got 1 squared, which is just 1, and then plus 2 times 1 times I, so just plus 2I, and then plus I squared. And I squared we'll be able to simplify. I squared is just negative 1. So this comes out to 1 plus 2I minus 1, and then the 1's and the minus 1 cancels out, and we just have 2I. So using that, we can come up with a square root fact for the complex number 2I. The square root of 2I, based on this fact, it looks like it should be just 1 plus I. But we should also consider the negative case. Of course, we know that negative of 1 plus I, if we square that number, well, it just comes out to the same result because negative times a negative cancels itself out. So negative of 1 plus I, that quantity squared, is the same as just 1 plus I squared, which we already saw is 2I. Now, unlike for the real numbers, where we could say that negative 3 is less than 3, there is no natural ordering for the complex numbers. Meaning that it doesn't really make sense to say that the negative of this complex number 1 plus I is less than the complex number 1 plus I. That doesn't really make sense to say. Likewise, it doesn't make sense to say it the other way either. 1 plus I. It doesn't make sense to say it's greater. That's not right either. It just that there's no natural ordering that's defined for the complex numbers. So as a result of that, we just take the square root of a complex number to mean both plus or minus of this number 1 plus I. So plus or minus of that quantity. So we've really got two solutions for the square root of a complex number, because squaring either one yields that complex number, and there's no natural ordering that we can use to make a distinction between them. So there we go, we've got our first square root fact for a complex number. The square root of 2I is equal to plus or minus of 1 plus I. Now, of course, this was kind of cheating because we started with 1 plus I and then squared it to figure out what number should go in the root. Usually when we take a square root, we want to start with the number inside of the root and then take the square root of that. So we'll learn how to work this process the other way, starting with the number inside the root and then figuring out what squared makes that. We'll learn how to do that in the next slide. Alright, so here's an example of a more difficult problem. We want to find the square roots of negative 8 plus 6I. So this time we're starting with the number inside the root and we have to figure out what complex number squared gives this. Okay, so why don't we write this down? We want to find the root of negative 8 plus 6I. And we know that that's going to come out to plus or minus of some complex number. Why don't we call it x plus I y? Alright, so now let's go ahead and manipulate this equation to figure out what x and y are here. So what if we square both sides of this equation? Then we just get negative 8 plus 6i equals x plus iy squared. The squared cancels out the plus or minus, and this makes perfect sense. If the root of this complex number is that complex number, then the square of that complex number is this complex number inside the root. Now, why don't we go ahead and multiply out the right-hand side here. So x plus iy squared, that comes out to x squared, then plus 2 times x times iy, and then plus iy, that quantity squared. We can simplify that even more. That's x squared, then plus 2xy I, and then I squared is -1, so we've got a minus, and then y squared. Let's just group that up. That's equal to x squared minus y squared plus 2xyi, and that has to be equal to -8 plus 6i. Now this might look kind of tricky. It looks like a single equation with two unknowns. How do we solve it? Well, there's one thing that we can do. We can introduce the constraint that x and y are real. Any complex number we can write as a real number plus I times another real number. And what that does is that introduces two parts to this equation. There's a real part and there's an imaginary part. The real part is that this -8, which is real, has to be equal to this x squared minus y squared, which is also real. So we've got that real equation, -8 equals x squared minus y squared. And by the same token, we've also got an imaginary equation. This 6i here is imaginary, and then this 2xyi is also imaginary. So we've also got an imaginary equation that goes 6i is equal to 2xyi. And now these two equations form a system of two equations in two unknowns. And we can solve that. The way we can solve that is we can solve for one of the variables in terms of the other in one of these equations and then sub it into the other equation. So which equation is easier to solve for one of the variables? I think this imaginary equation is easier to solve for one of the variables in terms of the other because we don't have any squares or anything. Both x and y are raised to a single power. So why don't we solve for y in terms of x in the imaginary equation, and then we'll plug that into the real equation. Okay, so let's do that. So why don't we first clean up the imaginary equation. We've got an I on both sides, so we can divide out by I, get 6 equals 2xy, and then we can just divide by 2 on both sides, get 3 equals xy, and then to solve for y, we just divide by x. So we get that y is equal to 3 over x. Great, so then we can substitute that into the real equation. Let's go ahead and write that up here. Alright, so we'll have -8 equals x squared minus the quantity 3 over x squared. And now it's just up to us to solve this equation for x. Let's go ahead and do that. Let's just simplify first. -8 equals x squared minus 3 squared is 9, and then over x squared. To get the x squared out of the denominator, we can multiply both sides by x squared and get -8x squared is equal to x to the 4th minus 9. And now we can move all the terms to one side. How about let's get 0 equals x to the 4th plus 8x squared minus 9. And hey, we can factor that nicely. That becomes 0 equals x squared plus 9 times x squared minus 1. And then using the zero product property there, we've got two potential solutions. We've got one solution which is given by the equation x squared plus 9 equals 0. And then we've got another solution, which would be given by the equation x squared minus 1 equals 0. So this solution here, x squared plus 9 equals 0, we get x squared equals negative 9. And then taking plus or minus square root, we get x equals plus or minus square root of negative 9. But that's an imaginary number because that's a negative inside the square root, and we know that x is supposed to be real. So this equation here has no real solutions. But that's okay, because we've got another equation, x squared minus 1 equals 0, that should give us some real solutions. So let's go ahead and solve that. X squared has to equal 1 then, so x is equal to plus or minus square root of 1, so plus or minus 1. Great, so now that we know that x equals positive 1, or x equals negative 1, we can use each of these solutions for x to figure out what y is in each of these cases. If x equals 1, then y equals, since y is just 3 over x, y equals 3 over 1, which is just 3. Or if x equals negative 1, then y equals 3 over negative 1, which is just negative 3. So this brings us to our solutions. X plus iy are the complex numbers. So in this case, x is 1, y is 3, we get 1 plus 3i. In the other case, we get negative 1 minus 3i. So putting these two together, we can write that the solutions are just plus or minus 1 plus 3i. And there we go. There is the final solution. And this method here of assuming a complex number of the form x plus iy, where x and y are real, and then breaking up into real and imaginary system of equations and solving that system, that'll work for any complex number. So we can use this method to find the square root of any complex number. Great, so now that we know how to find the square roots of complex numbers, in the future we'll continue to learn how to perform other operations with complex numbers, such as division.